Welcome back to another explainer. If you are a graduate engineer just stepping into the offshore industry, you are in the exact right place. Today, we're bringing you a masterclass. We are going to take a deep dive into the fascinating, high-stakes world of offshore electrical design. We're going to explore exactly how we determine the electrical heartbeat of an entire facility. So, imagine this. Someone hands you a completely blank sheet of paper and says, "Go ahead. Design the electrical system for a brand new offshore oil platform." Where do you even start? Before you can size a single cable, pick out a transformer, or specify any piece of switchgear, you have to find one fundamental number. And that's the total electrical load. Everything starts right there. And honestly, the stakes here could not be higher. That total load number, nobody is just going to hand it to you. You have to rigorously calculate it from the ground up. If you get it wrong, you're looking at two pretty catastrophic outcomes. Either you build a system that trips under load on day one of operation, literally shutting down all production, or you waste millions of dollars buying massively oversized equipment that the platform never actually needed. Okay, let's dive into our workflow for today. We'll start with 1, the blank page problem. Then 2, building the load schedule. 3, adding crucial motor margins. 4, power factor and generator sizing. And finally, 5, selecting the right generators. Let's kick things off with Section 1, the blank page problem, the engineer's dilemma. Moving right along to Section 2, building the load schedule. This is your foundation. The master load schedule is our absolute starting point for estimating total power consumption. You have to remember, offshore platforms are basically self-contained cities, right? Every single power-consuming device needs to be accounted for. From this one document, we'll eventually decide how many generators to install and what the highest voltage should be for the whole power system. Notice how engineers have to categorize every single piece of equipment into continuous, intermittent, and standby power? For example, take the potable water pumps. They're listed as 5 kilowatts continuous, 5 intermittent, and 0 standby. But then look at the instrument air compressor. That's 90 kilowatts continuous and 90 standby. You definitely don't just add everything up blindly. To find the true normal running load of a switchboard, you take 100% of the continuous load, add a fraction, usually about 50% of the intermittent load, and then maybe just 10% of the standby load. Which brings us to Section 3, adding crucial motor margins. We really want to avoid the classic rookie trap here. Here is a massive rookie mistake, simply looking at the raw mechanical power required by the driven machines and dropping those nameplate ratings straight into your load schedule. You can't do that. You have to apply industry rules of thumb. The motor rating absolutely must exceed the machine's base requirement by a specific margin. If your driven machine power is up to 15 kilowatts, you apply a 125% margin. For 16 to 55 kilowatts, it's 115%, and for the really heavy machinery above 55 kilowatts, you're going to use a 110% margin. Let's actually look at how this plays out mathematically. Say you've got an instrument air compressor that requires 90 kilowatts of mechanical power. That falls into the above 55 kilowatts category. So we take 90 kilowatts, multiply it by our 1.10 margin, and we get 99 kilowatts. But here's the thing. You can't just run out and buy a custom 99 kilowatt motor. You have to select the next standard motor size available on the market, which happens to be a 110 kilowatts. So the absolute crucial takeaway here is that 110 kilowatts is what actually goes into your load schedule, not 90. All right, pay close attention to this next part. Section 4, power factor and generator sizing. This is the critical conversion. So your master load schedule is all filled out, and it's giving you your active power in kilowatts, or kW. But here's the catch. Generators aren't rated in just kilowatts. They are rated in kilovolt amps, or kVA, which represents apparent power. You cannot directly equate those two numbers. Connecting them requires a really critical conversion step. And here is the core conversion formula for sizing your generator. It's incredibly straightforward, but it fundamentally dictates the size of the massive multi-million-dollar machines you're going to place on your offshore platform. Generator kVA equals total kW divided by the power factor. To really understand what's happening here, it brilliantly helps to look at the power triangle. On the horizontal axis, we have our active power in kilowatts. That's the actual physical work being done by our motors. On the vertical axis, we have our reactive power in kVAR. Think of that as the power required just to sustain the magnetic fields inside those induction motors. Geometrically, these form a right triangle where the hypotenuse is our apparent power, or kVA. The angle between them, often called phi, represents our power factor. Now, since oil industry plants operate predominantly with induction motors, they naturally run at what we call a lagging power factor.
So how do we estimate this power factor before the plant is even built? We use assumed constants. As you can see, it is standard industry practice to assume an overall power factor of 0.87 lagging for low voltage or LV switchboards and 0.89 lagging for high voltage or HV switchboards. Seriously, lock these numbers in your mind right now. They are completely essential for your early design calculations.
Moving to our final step, Section 5, selecting the right generators and the N-1 capacity rule. All right, we have our freshly calculated total kVA. Now, we have to select the actual physical machines to install on the platform, and we do this using the N-1 capacity rule. Remember, offshore platforms are completely isolated. If a generator goes down for maintenance or a fault, you can't exactly plug an extension cord into the local grid. So, if your total power consumption is 15 megawatts, you might install 5 generators rated at 5 megawatts each. That N-1 rule ensures that if one of those 5 generators totally fails, the remaining 4 units can still comfortably handle the entire load, typically operating somewhere between 66.7% and 90% of their total capacity. It is all about maintaining continuous, safe operation no matter what. Which leaves us with one final, incredibly important question. What happens to all of these tightly optimized load calculations when the oil platform inevitably undergoes a major modification 5 or 10 years from now? Because engineering is never static. A really good rule of thumb is to always assume between 15 and 25% extra capacity will be required for future growth. So how are you going to future-proof your next design so you don't paint yourself into a corner? It's definitely something to think about as you start your engineering journey. Thanks so much for joining me on this explainer, and I will catch you in the next one.